Hello, I'm Cadence Lorio, and the first FRQ we have is on slope fields. The first question is, on the axis provided, sketch a slope for the given differential equation at the 6 points indicated. The slope is given by the differential equation 2x minus y. So what we're going to do is plug in x and y points for each point to find the slope at that point. So we have, for 0, negative 1, it's going to be 2, 0, plus 1 because it's negative. So that's going to be a slope of 1. So that's basically that. Then we're going to have 2, 0, minus 1 for this point, and that's going to be negative 1. So it's going to be the same slope, just downwards. Then we're going to have 2, 0, minus 2. That's going to be a slope of negative 2. So that's going to be steeper. And make sure to have it thick and long. Now we're going to do these points. So the next point is going to be 2, 1, minus 0. And that's going to be, minus 1, sorry. So that's going to be 1. So it's going to be the same slope as this at this point. Then we're going to have 2, 1, minus. It should be plus 1, sorry, because it's a negative 1. So the slope is going to be negative 1 at this point. Now this point is going to be 1. Then we're going to have 2, 1, minus 2. Right? Yeah. So it's going to be a slope of 0. And that's going to be a horizontal line. Make sure to have it thick and long to make sure the slopes are clear.
Why is the slope, when the slope is 0, why is it a horizontal line?
Because when you have rise over run, dy over dx, you're going to have basically 2 minus 2 divided by 1 minus 1. So when you ever divide, wait. I'm going to edit that out. So when you have a horizontal slope, it's usually rise over run. Whenever the rise is 0, since you're not moving upwards at any point, it's just going to be 0 for rise. And run, the x is always changing, so it's going to be 0, infinity. So the slope is always going to be 0 because anything divided by 0 is, 0 divided by anything is 0.
I see. Go.
All right, Professor DK back at it again. So our second question is, find the second derivative in terms of x and y, determine the concavity of all solution curves for the differential equation in quadrant 2. Give a reason for your answer. So if you recall to the beginning, our original equation is dy dx equals 2x minus y. Now, this is telling us to go to the second derivative, so we'll rewrite this. And the derivative of 2x is 2, and the derivative of y is dy dx. Now, we don't know what dy dx, but we have the equation, so we'll plug in this equation for dy dx. So we'll get 2 minus the quantity of 2x minus y. Now from here, we're going to plug in a point from the second quadrant. Which is located over here. So let's say our first point will be negative 1, 1. So plugging it back into this equation, you'll get negative 3 in here, sign becomes positive, and you'll get 5. So your value in the second quadrant will be positive. Now we're going to test it at another point just to be sure. So our next point will, let's say, be negative 2, 1. as you can see, it is also positive. So it's safe to say that the concavity in the second quadrant will be positive, because d squared y over dx, that can be written as y double prime. And using what we've learned in class with the relationship between f prime, and f double prime, if f prime, or in this case y prime, is positive, you have f is concave up, and these values are positive. So therefore, the concavity in the second quadrant of the differential equation is concave up.
Go.
All right, Professor DK at it again, and our third question is, let y equals f of x be the particular solution to the differential equation with the initial condition f of 2 equals 3. Does f have a relative minimum, a relative maximum, or neither at x equals 2? Justify your answer. So we're given the equation already. dy dx equals 2x minus y. Now that's already to the first derivative, and if you recall back to the relationship between f prime, and f double prime, f has a relative minimum when f prime changes from negative to positive, and relative maximum positive to negative. However, for that to happen, f prime has to cross the x-axis. So that means at this point, at this condition, it should equal to 0. So we're gonna plug these points into the equation and see if it equals to 0. So that is the equivalent of this. So as you can see, at 2, 3, the first derivative does not cross the x-axis. Therefore, there cannot be a relative minimum or a relative maximum.
Alright, this is Professor Gerardo, and we're here with problem D. And it states, find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. Okay, so to start off, our differential equation is dy over dx is equal to 2x minus y. So we have that. And a solution is y equals mx plus b. In order to find that solution, we must take the derivative of this to be able to equate it to this. So the derivative of y equals mx plus b is simply m, because that's a constant, and x, so m. So now what we do is, we have 2x minus y is equal to m, right? At this point, what we do, since we have y is actually mx plus b, so we're going to plug in y equals mx plus b for that y. So what we end up getting is 2x minus mx plus b is equal to m. At this point, we want to solve for m, right? So we can find our first constant, which is m. To do so, we must get this on the other side and equate this function to 0. So you get 2x, and let's distribute the negative sign to make everything easy. 2x minus mx minus b minus m is equal to 0. And what we want to do here, since these two have a common term, which is x, we'll group them. We'll group these two, and we'll group these two. So simply, we get 2, and we're going to take out whatever's common, 2 minus m, parentheses, x, and then minus minus, we can just do minus m plus b is equal to 0. Okay, so now we have two separate parts to this equation. Our first problem is to find m. So to find m simply, all you have to do is equate 2 minus m is equal to 0. So 0 equals 2 minus m. This is simple math, just subtract 2 from both sides. Negative 2 is equal to negative m. Divide both sides by negative 1. And you get m is equal to 2. Now that you have m is equal to 2, you can simply find b by plugging it into this part of the equation right here. So you get m equal to 2, and then so 2 plus b is equal to 0. To find b, simply subtract 2 from both sides. You get b is equal to negative 2. So we have both of our constants that form the solution to this differential equation. Any questions?
At your first step, why did you plug in mx plus b into y? Why didn't you just make it in a form of y equals mx plus b?
Well, to plug in, it's much simpler to plug it in because we can work with terms that are like x, and we have m, and we want to find m. So you might as well use x and x instead of y, because y is a whole different variable, and it would have 3 variables. Instead of having 3 variables, we can use 2 by replacing y with m, x, and b. B is not important variable at this time, so all you have to really focus on is x and m. We get rid of y, and we don't have to use b because it's a constant.